Hello everybody. In today's video we are going to discuss about operator precedence parser. So this is a special parser for programming languages which deals with parsing of expressions. Now expressions are very important part of any programming language construct. So you may have mathematical expressions, a plus b into c. You may have logical, a is greater than b. You may have relational expressions. Okay, this is a relational expression. This one here can be a logical expression. Okay, so you have these different types of expressions, and in these expressions what is common are your operators. So every programming language consists of a number of operators. So these operators, the grammar for these operators are slightly different as compared to the grammar of the other programming constructs. And so there is a special parser for parsing of these expressions. So let us see what this is. So as I have mentioned that we are going to look at the operator precedence grammar, precedence parser. And the type of grammar which relates to these expressions and operators, this is known as a operator grammar. Operator grammar. So a operator precedence parser will work only on operator grammar. So what is this operator grammar? It is a grammar which follows two simple rules. The first one says that no two non-terminals appear together in the grammar. That means if I have a production like this, A derives say B, C star, okay, this is not a operator grammar because the two non-terminals B and C, they appear together. So you cannot have an operator grammar like this with productions like this. Similarly, I cannot have something like this. Say we are using the same convention. We are using the convention that capital letters they represent non-terminals and small letters represent your terminal symbols. So if I have a grammar like this, you see, this is not operator grammar because here more than one non-terminals appear together. So, and also the second rule is that there are no epsilon productions. So you cannot have a production like this, say A derives epsilon. So no production of this type should appear. So if these two rules are satisfied, in that case you have the grammar that you have is a operator grammar. So now here in this particular grammar, you can see that I have to, this is not operator precedence grammar, but what we can do is we can convert it into a operator grammar. How? If I replace this B by the non-terminals, by the terminal symbols that it represents. So I can have productions like this. I had S derives A, B, C and B derives plus or multiply. Okay, so I can rewrite this as S, I will replace B. Okay, so I can replace B by plus, or I can also replace B by star. So I get these two productions. So now this grammar that I have got here, this is a operator grammar. This is the operator grammar. This one here is not an operator grammar. So we can rewrite the grammar to make it an operator grammar. Also, another thing that is that the operator precedence grammar can work, parser can work on, is that it can work on ambiguous grammars. Ambiguous grammar. So it can work on these ambiguous grammars also. Okay, so here if you see this grammar, this is ambiguous. Okay, so but you can still have a operator precedence grammar, operator precedence parser, sorry, which can parse this particular grammar. So let's see the steps. So the first step that we do is we construct a table known as the operator precedence table. Operator precedence table. So in this table what we have is we have rows and columns. So along the rows we list out all the operators, and same way we list out all the operators along the same operators along the columns. So all the non-terminals are going to be listed out here. When I'm saying operator, I mean all the terminal symbols, and the special symbol $. The dollar symbol, the end of the string, dollar symbol is also added. So if I have, say my grammar is, let me take this grammar, E derives E plus E, E minus E, E into E, E into E, or E divided by E, or ID. This is my grammar. So here I have the operators plus, minus, multiply, divide, and ID. These are my terminals. So I will have rows and columns for each of these. So I put, say, ID, then plus, minus, multiply, divide, and $. Okay, there's no order to be maintained, but you have to you can put it in the same manner here along the row also. So plus, minus, multiply, divide, and $. So now we have to fill up this cell. We have to fill up each of these cells. Okay, so I have all of these rows and columns. We have to fill up the cells of this table. So let's say ID and ID. So if it is ID and ID, ID and ID is the same thing. So we are just going to put a mark here. This means that two IDs can never appear together in an expression. So if I have a mathematical expression or some expression, I cannot have ID and ID together like this. So you can say that ID and ID will never appear. Now out of all these, ID always has the highest precedence. Okay, so highest is ID and lowest precedence is $. This you keep in mind. So if suppose I have an entry like this, so X is along the row and Y is along the say the column, okay, and the precedence of X is greater than Y, then we put this. We put the symbol in the cell. Again, let me repeat. X is higher, by higher I mean the precedence, than Y. Okay, so if X is higher than Y, then we use this symbol. But if X is less than Y, precedence of X is less than precedence of Y, then we use this. Okay, so X is less than Y. Okay, and if they're equal, then we put equal. Okay, X is same as Y. Now here there is a catch, that if X is same as Y, if you say plus and minus, they have the same precedence in a programming language like C. Okay, but when you have an expression which contains a plus and a minus, okay, in that case, the one which is, because of the associativity, even though plus and minus have the same precedence, because of associativity, the left plus will be done first as compared to the minus on the right hand side. The same applies if I have plus plus also. So I have x plus y plus z. So because of associativity, I know that x plus y will be done first. Then with this, I will find the sum of z, add z to it. So this plus, the left plus, has higher precedence than the right plus. So in that case, if I have plus plus, say, even though these two are equal, plus here, this plus which is on the left will have higher precedence than the plus on the right. So I will have this particular sign will be there. So let us go back to our grammar and try to fill up this table. Okay. So from our grammar that we have, you can see that this is an ambiguous grammar. This is also an operator grammar because no two non-terminals appear together, and there are no epsilon transitions or epsilon productions. So we will fill up this table. So ID and ID. So ID, ID. So as I said, no two IDs will appear together. So this is an error cell. If this happens, then you have to mark an error. Then remember I said ID has the highest precedence. So ID will be greater than everything else. So ID is greater than everything else. Then plus and ID. So plus ID here. So everything here would be, everything on this side would be less than ID. So less than, less than, less than, less than, less than. Okay. Now look at this plus and plus. So this is our x and this is our y. So plus and plus, they have the same precedence, but associativity is left to right. So x is the left one. So you say x is greater than y. Similarly, plus minus, same precedence, but left associative. So plus is greater than minus. But plus and multiply has got higher precedence. So plus is less than multiply. Remember, we are looking at it from x, comma, y pair. So x is on the left side, y is on the right side. So we are comparing if x, precedence of x is greater than precedence of y. So here, precedence of plus is less than precedence of multiply. Same here. Okay, but dollar here has the lowest symbol, lowest precedence. So plus is greater than dollar. So minus and plus. So okay, now this minus will get higher. Minus is higher precedence. Minus minus, this left hand side will have higher precedence. Minus and plus, multiply will have higher precedence. Minus and division higher, but minus and dollar, minus will have higher. Same here, dollar, star and plus, star will have higher. Star and minus, star is higher. Star and star, same precedence, left associativity. So this star will have higher. Then star and division, same precedence, but star is on the left hand side. Okay, and star is greater than dollar. Same for division. Division is greater than plus, minus, and again left hand side, so it is greater than this. Left hand side, so it is greater than division. And of course it is greater than dollar. And dollar is less than everything else. So less than everything else. And dollar, when we say this is what? This is except. This is error. And this is except. Because when you get dollar, then your parsing stack is empty and your input string has also been exhausted. So this is the table. So first thing that we have to do given a grammar is, first of all, we have to check if it is your operator grammar. If not, we have to convert it into operator grammar and construct this operator relation table or operator precedence table. Next, we go on to the actual parsing algorithm.